Hi, everybody. I'm Joe DeVivo. I'm going to talk to you about HTTP2 and my Erlang library for it. I guess the coolest thing I'm doing right now is I'm actually serving up this slide deck through HTTP2, so we're going to refresh it real quick. We got a little lightning bolt up there. That means it's working. And I've got a bunch of log messages that show that same thing, so you can believe me or you can download it later and see for yourself. Let's see, to do this right, I have to, this is the one consequence of doing a full screen browser-based presentation is I have to drag it down there, but I have now, so we're good. All right, so my library is called Chatterbox. There's a link to the code. There's a link to the deck. The deck is, you can't see the red here, but it is joedevivo.com/EUC2015, so you go look at this deck right now. Let's talk about HTTP1 before we talk about HTTP2. It's huge. Every one of you has touched it today. Just in your life. It's everywhere. And it is a very, very well-defined thing. The Remix HTTP 1.1 spec that came out last year is 292 total pages, actually 6 RFCs, and you can find all the links in this deck somewhere. And it's a big deal, and everybody's really looked at it. It's kind of not really economical with TCP. It keeps connections alive, which is good. We don't want to open these things all up, and that's a big improvement over HTTP 1, so that 1.0, so that's something. But it sequentially sends requests and receives responses in order via pipelining, and that can be bad if you're not responsible. That introduces this idea of a problem called head-of-line blocking. And what that does is, you can send as many requests as you want over a single connection, but the first one is going to respond first, and until that response is served, that's it. We're all just waiting. And there are lots of people that have hacked lots of ways around it, and I don't even want to talk about them because they're all terrible. They're okay. But transfer sizes are going up, and transfer quantities are going up. So head-of-line blocking is just going to get a bigger and bigger problem, except that browsers don't even implement it. So a lot of HTTP 1.1 was optional, and that causes a lot of problems when you're developing software that's supposed to work together. So that's where HTTP 2 comes in. Here's the abstract, and I don't expect you to read it here and now, but I highlighted these parts in gold and then turned them into bullet points so we can talk about them. The goal of the protocol is to be more efficient with network resources. It wants to reduce the perception of latency in web applications. It does this via header field compression, allowing multiple connections, concurrent exchanges on the same connection. This new feature, which is this unsolicited push of representations from servers, and it uses HTTP's existing semantics. These bullet points are verbatim from the spec. So this was the idea, and Google tried it with Speedy, and they pretty much proved that it could work, but it was all Google all the time, and nobody wants to just go to the Google show and not do anything else. So the HTTP working group eventually sort of, got ideas from Google and people from Google, and they did their own thing too, and it became this bigger open thing. And HTTP2, the RFC, came out and was fully approved and finalized just last month. And what it gives you is the ability to keep your HTTP semantics, gives you a path to upgrading HTTP 1 requests, or messages as a whole, and it lets you be more efficient with connection and networking. And did I mention server push, the new feature, as it were? But it is another feature designed with these 3 things in mind. So you want to keep your semantics, and these are get, post, and all of his friends, and headers, request and response headers, request messages, response messages. These are the things that a programmer uses to use HTTP, like API levels, browsers use them, and we're going to keep using them. Which technically means these 5 RFCs from HTTP 1 and some of that 6th one are all still valid. So if you thought you got out of reading that 292 pages, well, you did because you're here and we're talking. But it is quite a read. And from the Erlang perspective, that means something like WebMachine. We can take a the module that we use for WebMachine right now is MochiWeb, and MochiWeb will, does the HTTP serving, and then WebMachine does the rest part, the REST, not the remainder. But we can plug in something like Chatterbox to WebMachine at a certain API level because the semantics of HTTP have unchanged. Let's talk about upgrading HTTP 1 requests. It's probably the simplest part, especially since I didn't do it. My implementation is not done. So watch this space as we keep going. But HTTP 1 requests can be upgraded one of 2 ways. If it's coming over HTTPS, then it uses TLS's either the next protocol negotiation or the application layer protocol negotiation. And it uses NPN because Speedy uses NPN, and they say, okay, it's fine, we'll still do that, but they don't really want you to, and Chrome's dropping support for NPN and Speedy, so everybody's moving to HTTP2 and ALPN. I believe Erlang 17's on NPN, and 18 will be on ALPN, so I'm on 17 now, so we're still using NPN, but it's the future, ALPN. If it's just a plain text HTTP connection, first of all, they discourage it. Firefox and Chrome are both only doing HTTPS support for HTTP2, but they just couldn't quite convince everybody that you had to be SSL or bust. So if you're doing a clear text HTTP2 connection and you want to upgrade from HTTP1, there's this 101 switching code, which came out really small on the slide. But and then you can go into an upgrade. And that actually winds up creating a second connection, but using 2 connections for your entire session is better than like 1 million, so that's good. So let's talk about networking optimizations, and a big one is, comes from header compression. And one of the bigger things that we have to worry about with HTTP is that it's a stateless protocol. And stateless protocols are repetitive. And if you don't believe me, stateless protocols are repetitive. So they came out with a whole nother RFC. It's like another 60 pages. I got 20 pages into the HTTP2 spec, and then it's like, oh, just see this other RFC for header compression and move on. And then you get to that RFC, and it's another 60 pages. But it's actually really cool, and it's a much smaller problem. Well, it's a subset of HTTP2's problem, right? But what it does is it introduces the idea of a stateful compression context on the connection level. So let's talk about what a compression context is. And it's essentially, here I wrote this down so you can see it. It's a lookup table for common and recently used headers. And the initial state for this thing is called what they call the static table. And the static table is a set of 61 of the most common headers. And they did some analysis over a bunch of web requests, and they basically said these are all happening a lot. Some of them have corresponding values like path and slash, for example. That sounds pretty common, right? Response 200, that's very common. Others don't have values at all, like user agent, which is a very common header, but there's not really one very common value for it. I mean, even if it's Chrome, it's still Chrome 1.37.million.build 32, whatever. So we don't have one there. But that's what the static table looks like, and every compression context when it starts looks like that. Of course, in Erlang, that looks like this, which is a 3-tuple. It's got an index, a value, and a name, or a name and a value, sometimes a value anyway. You might have noticed these pseudo headers. Method, path, scheme, and status aren't headers in HTTP1, and they're not really headers in HTTP2. But we're using this header context to keep track of them. So we're still going to we're going to use these. We're going to treat them like headers at the implementation level, but they're not really. So yeah, like I said, the initial context of this value is the static table, but there's more. There's this idea of the dynamic table. So like I said, indexes 1 through 61 are all specified by the spec, and they never change. But you can add your own, and they come in at index 62, always at index 62. Everything increases, and it's a FIFO kind of thing, but we'll get into that right now. Also, the size of this dynamic table is bounded by the HTTP2 settings, so the connection sort of agrees, okay, this is how big we're going to let this thing get, and that helps prevent things like the crime attack. So what that's look like? Yeah. I have this idea of header names and header values, and then you basically have this dynamic table, which is just that 3-tuple that I showed you before, a list of those, and it's got sizes that we do the security checks with. And then we have this encode and decode function, and they're basically the inverse of each other, right? Encode takes a list of headers and returns a context because the context changes with every header you encode, and decode works the same way. You take a binary encoded block of headers, and out you get a list of all the headers that were sent over there. So let's look at this identity operation on a set of headers. If you put something in the set of headers that's already in the context, it doesn't change. You already have essentially an alias for this thing. So I've done something here twice. I've done an encode here on status 200, and then I've done a decode on the binary created by that. And when you are done, these two values are the same. So static table is this variable that I've bound up here to this new encode context. None of these bindings fail because it's all the same object, or the same data structure all the time. But if it's not already in there, things change. See, I'm trying to encode this new status code 600, which I think is going to be all the rage. And I've tried to put it in this context, and now the static table and the new context are not equal to each other. However, if I try to use that new context to encode status 600 again, now it is the same. Now this thing does bind correctly because once something is in the dynamic table, you look it up and it's there already. We don't need to encode it again. The context remains unchanged. But there's 4 contexts, because why would just one be enough, right? There's an encode context on the outbound request. There's an inbound context on the server side, right? So you've got headers going out from the client. They get encoded. Then encoded comes in on the server. They get decoded. We're both starting from the same common static table, so we all know what we're starting at. And as long as they stay in sync, everything's going to work out fine. And I tried to make that look like math, and you can read this slide later. I'm not going to explain it now. But basically, as long as these two things stay equal, everything's great. So here's a basic case for that. You've got this context A1, and you've got your set of request headers coming in. They get encoded over the wire. They come in on the server side. You decode them based on the static table, and you have your new set of headers. And that's really trivial. Why would you want to do any of that? Well, in a case where you're sending multiple requests over the same connection, it gets more interesting, right? All these sets of headers all go through this one context, and each time a set of headers goes through, the context changes. But the encode context and the decode context are both changing like lockstep, same set of requests coming in the same order. So these objects are always going to be basically the same representation on both the client and server, which allows you to say, well, I'll show you what it allows to say right now, because I'm going to show you how HPACK packs. There are 2 data structures in HPACK, numbers and strings. Numbers basically represent indexes that we talked about in those 2 tables, and strings are everything else. So let's talk about that. This is a single byte that comes over in a byte encoded header field. And if you're sending something as simple as like path/, then you just send the number 2 over the wire. Actually, it's going to be, the first bit is going to be 1, and the remainder of the bits is going to be 0, 0, 0, 0, 0, 1, 0. And you're sending over 1 byte to represent this, this more than 1 byte value. Now, you may have noticed if that number is going to be more than 2 to the 7th minus 1, that we got a problem here, and HPACK does a different way of representing integers larger than the space it has to fill. But this talk doesn't actually have the space to talk about that, so we're going to move on. So if you have something like user agent, where you need to send over a value because there is no value set up by default, then you have a different sort of byte prefix up there, or bit prefix for the first 2. And this lets HPACK know, okay, this thing is coming over with an index for the name of the header, but the value is going to be a string. So then I send over the index, and same thing, if 2 to the 6 minus 1 is too big to hold the index, then we have another way of representing it. And then we have the same thing here, another integer that says the string value for this thing is going to be this much longer afterwards, and then a bunch of octets that's that long. And then the last one, if we do a custom header that's not in any part of the context yet, we send over 2 strings. I mean, that's pretty easy, right? We just have this first byte that's all well-defined, mostly zeros, and then just 2 strings, name-value pairs, just like the old days. When a literal header does come over, there's a couple different prefixes that you can put on it just to tell HTTP2 how to route these things. Sometimes you don't want it to add things to the index, so we just say without indexing. Otherwise, we say with indexing. And never index just means if you're a proxy and you're going to tell your friends all about this request too, tell them not to index it either, because we don't want it indexed. We were never here. But what's cool about these things is that we can really just like pattern match like all day with these things. All this spec specifies, if the beginning of the byte is this bit, then we do that. If this byte is this, then we do that. And if the first 2 bytes are this, or the first 2 bits are 0, 1, then we do this. And if it's 0, 0, 0, 0, then we do that. And it makes really reading a binary protocol really fantastic. So binary pattern matching, get into it. You might have saw that like Huffman encoding was a thing that we could do with these string values, and we can. We're not going to here, but it's basically a statistically analyzed way of encoding strings that makes each character that is most commonly used, like in displayable characters, like take up fewer bits. It's all about economizing the wire here. There are tons of cool examples of HPACK in the HPACK spec, and I turned them into unit tests, so you can click this link and go check them out. But I'm walking you through an example of like a couple of HPACK requests just to show you like how this thing winds up saving a lot of space. So I'm going to send these 3 requests over, and they're all trivial. There's 3 name value pairs, and we're going to go over them one by one so you don't have to read them all now. Here's the first one. It's a request for path/. The user agent is my cool browser, and I'm sending over a custom header, X custom header with some custom value. So when I send that over the wire, Wireshark understands HTTP2 and tells me, okay, well, path/, we know that one. That's index 4, so we're just sending over the byte 4. Then we see user agent. Well, we know user agent is index 58 from the static table, but it doesn't have a value, so we're going to send over the string my cool browser. And then X custom header, we can't find that in any context, so we're going to go ahead and send over both the name and the value. So, you know, pretty byte heavy, especially that last header. So as these headers pass through the context, what you wind up happening is, first of all, you know, you try to put path in the context, and path is already there, so it doesn't do anything. Context remains unchanged. It's that identity operation we talked about earlier. User agent in my cool browser comes in, and we go, okay, well, this name value pair is now going to be 62 in the dynamic table. And that's great. Moving on, X custom header and some custom value is now going to be 62 because it's another new name value pair that we've seen. And so we bump everything that's in the dynamic table already up 1. Everything moves out towards the back because once you get too big for the agreed connection size, we drop things off the end. So keep good stuff at the beginning. It makes it easier to find. So great, now we're going to do another request to the same server. And it's going to be, you know, we're looking for some file, HTML. That's our path. The user agent and X custom headers have not changed. We're going to send over the same ones because it's a part of our session. We're in the same browser. X custom header might be some kind of cookie or auth token or whatever. So we Wireshark that. And look how much smaller the actual data we send over is. Path still matches up as a name to index 4, but we've never seen this value before, so we're going to go put that on the wire. But then my cool browser and user agent, we both know, both of us being the client and the server, that's index 64. And we both know that X custom header and some custom value are index 63. So now we're just sending over 1 byte for each of those second 2 header fields. So already we're saving a lot of bytes. A lot of bytes being saved here. Now, you may have noticed that I just said these were indexes 62 and 63, and now I'm saying they're indexes 63 and 64. What happened there? Well, path and / some file is a new name value pair combination. So as soon as that one set of headers came in, we saw it and went, all right, that's a new pair. We're putting it in the dynamic table as index 62. Everything got bumped up 1. Then when we looked for these other 2, they were already bumped up. So that's, and we all know that, so that's why they sent it all over. So then here's request 3. We got the same path, some file, HTML again. User agent's the same, and we've changed the value on X custom header. And what happens to the context is, well, path and some file HTML are now things that we've seen, so that's just index 62. It was index 62 on the last slide, and it's the first header coming in on this slide, so there's no index change at all. Same thing with user agent and my cool browser. Now, another cool thing that's happening here is X custom header has this new value, but we've already seen the name X custom header, and we know that's index 63, so we're already saving the bytes for the string X custom header. We only have to send over the binary new value. And that's what happens. And eventually what winds up happening is we see X custom header a new value, and that's a new thing. So it goes in the front of the dynamic table. Everything else gets +1, and we actually have 2 X custom header name value pairs in the dynamic table, and that's cool. Maybe we'll see either one of them again. Maybe we won't. Maybe we'll get so big we just dump them off the edge and we never see them again, but that's okay too. So that's HPACK. That's how HPACK works. Another real cool thing about HTTP2 is multiplexing. And multiplexing is pipelining done right. What it allows us to do is just send individual frames over the wire that are interleaved, and we just reconstruct the streams on the other side. So what's a stream? There's one connection, and streams are logical abstractions across it. They have unique identifiers. At most, there's 1 request and 1 response, but there doesn't necessarily have to be a request per stream. We'll get to that in a second. But client-initiated stream IDs are always odd. Except stream 0, which is the meta stream for the connection. Frames sent to it apply to the entire connection. If you want to negotiate settings on the connection level, how big can frames be, how big can dynamic tables be, these are things we talk about on the stream 0. So yeah, every frame has a stream identifier. That's how we know what to do with it, or where it goes at least. There's 1 stream ID per frame, and as these things come over the wire, we just reconstruct them on the other side, and we know what to do with them. We can reconstruct them in order. Why in order? Well, remember we just all talked about HPACK and all those indexes and how they changed and how they process headers in order? Well, if they come in out of order and you get two streams crossing like this, then what happens is you wind up with a bad header decode at best. At worst, it just doesn't even know what to do with itself and crashes. Or it sends a protocol error because we can send protocol errors now. So just to sum up the jargon here, a connection has multiple streams, each of which can accept a single request message and send a single response message, each message consisting of multiple frames in order. So how do they handle them? Well, there are rules in the spec about how many connections can be active simultaneously and what kind of frames can be accepted when. And they gave us this cool diagram in the spec. And I got excited because I'm like, oh my God, it's an FSM, and I can make a Gen FSM, and I'm in Erlang, and it's perfect. So don't get your hopes up. That's not what happens. But a frame does look like this. Each frame has a 9-octet header, the first 3 of which are just length. And that is the length of the payload. The 9 octets are not included in that. Following that is a type. There are 10 types of frames, and each has rules for how big the payload can be or not. Some of them don't. What's in the payload and what flags can be set. So what do I mean flags? Well, flags is the next byte in the header. And it's just 8 bits that you can just flip for various reasons based on what type of frame it is. Then there's this one reserved bit that does absolutely nothing. It's in the spec. It says ignore it, so ignore it. But the next 31 bits are the stream identifier. And that means you can only have 2 to the 31 minus 1 streams over a connection. So if you ever use that many streams, we close the connection on you. Sorry, but you've had a really good run with this connection, so you should be happy that you didn't waste all those other connections. And look, it's so easy to binary pattern match this thing and just construct a record of a frame header. I mean, look at that. That's it. That's all I do. Yeah. So like I said, there are a couple of connection level type frames, and I'll talk about them real quick. There are settings, and these the protocol negotiates these right at the beginning of the connection, but they can be changed at any time as well. There's a ping, which from the spec says it's used there to measure network latency. But in practicality, when I was watching Firefox actually serve up this thing, this deck over Wireshark, I noticed pings coming in every so often. And Firefox is actually using ping to keep the connection open for a while. And then after like 4 or 5 pings and it still hasn't gotten anything responses, then it closes the connection. It closes it with this thing called a go away frame. And it just sends it and it says like, bye, we're done. You know, sometimes it's bad and sometimes it's good. I mean, you can just be done. Sometimes it's time. Then there are stream level frame types, and these things are going to kind of look familiar, like headers, right? You send headers. We still have to send headers. Headers aren't going anywhere because HTTP1 semantics aren't going anywhere. And we encode this block fragment with the HPACK encoding, and we send this frame over the wire, and that's how this thing sort of knows, okay, we're starting a new stream with a new request coming in. Now, we talked about frame size as something you can set on the connection level. If your header block fragment is too big to fit in a header frame, we have this continuation frame, and we just put the rest in there. So we break up the header block into fragments based on frame size and send continuations over after the first headers block. So headers frame basically says, okay, we're starting, here's a message we're starting, and it's got headers. And then if it doesn't have its end headers flag set, then continuation is like, okay, here's the rest of it, here's the rest of it, here's the rest of it. Once end headers is done, you can send over data frames. And this is like your post body. But at any time, if you feel like this connection is just done and we've broken something, we don't want to wait for it to respond, we just want you to stop, we have reset stream. So we can actually say, okay, we're done, and you don't need to spin on this anymore, which is nice. So here's a sample message, right? It's just a headers frame, a couple continuations, one with the end headers bit flipped, then a couple of data frames, and an end stream bit. These are not all flags. And so as these frames come in and you process them, you can sort of pattern match on these things and be like, all right, okay, now I transition into this state where I can only accept pings now while we wait to serve up this response. So what do we do with routing individual frames? Well, I do actually have a Gen FSM, and it's called HTTP2 connection, and this monitors the entire connection state, and it basically owns the socket, and it owns all these connection settings, and it does all these checks on that. And one of these functions in it is this route frame function. Here's a real simple example clause of it. What I'm doing here is I have a receive setting that says this is the maximum frame size I can take, this MFS thing here. And if the frame header's length L is greater than that, then we go away with a frame size error. That's real easy. The spec says it somewhere. Maybe it says it like 8 times. I don't know. It's a spec.
So that's an example of how to route something at the connection level. But we also have these streams, and this was that thing that looked like that Gen FSM, and we were so excited we were going to get to implement it, and I was excited too. But it wound up being a different kind of FSM. I made this, I don't know, people have done this before, but I called it a phone height state machine, and I thought I was brilliant. But what it is, the idea is that it's a Gen FSM without the Gen. It's got no PID. It's not being spawned. And I'll tell you why we can't spawn it later. But this is a reminder of what it looks like. You've got these, what are we looking at, 7 states. And you can see they transition on sends and receives of certain types of frames. Or there's a glossary for this in the spec, but sometimes it's like send H, receive H, that's headers. But sometimes it's like send ES, that's end stream flag set. That can be set on a headers frame with no body on a request, or it can be sent on a data frame signifying the end of the request body. So, yeah, there you go. And these states exist on both sides of the connection, right? The client has it and the server has it. They keep track of every stream. So I had this stream state, and it keeps track of those state names, and it has a stream ID. And it will grow over time as we add more features. But it has these 2 functions for transitioning. It has a send frame and a receive frame function, and it sort of can model that diagram that we had before. So let's talk about what happens when a headers frame actually comes in. What we do is we have a, no, I'm looking at the future slide, but here it is. So this route frame function is at the connection level, and it gets a headers frame that comes in. And we have to check stuff like, what are the receive window sizes and stuff like that. Why do we do that here? I don't know. That's a different part of the talk. But we do here, we check the frame header type as headers. We check that it's got an end headers flag, and I use this is flag macro thing to make that easier, but it's just a binary and with some other math thrown on it, but it's real quick. So if this is a headers frame and it's the entire header block, we go ahead and we HPACK decode it. We use the decode context that's up there in the connection state, and then we create a new stream based on the stream ID from the frame, because we know it's the first frame in a connection. So we've done that, and now we need this HTTP2 stream, which is the state machine without a process. And what we do is we use this new method just to create it with its initial state, and it returns a state back to us. Then, back in the connection route frame function, the next thing we do is we pass this stream in along with our connection state, because some frames that come over the wire actually will affect overall connection state. So we have to make sure we have both of those things available to us to transition when we process the receive frame function. So what does this receive frame function do? Well, when it's a headers frame, what we do is we check and see if the end stream flag is set. If it is, we transition straight from the idle state, which is the first state, through open all the way into half closed remote. And that essentially means we're not getting anything more from the remote connection. We're still going to send some stuff back. That's why it's half closed. And then we have another thing here that's basically the catch-all. If those flags aren't set, then we're going to store this header frame as an incoming frame in case it winds up having a continuation frame. We just have to keep track of all these states. It gets very complicated. So this is the end stream case that we're processing. We know to run the content handler, which is what we're doing here. Handler is actually a thing that we can put in the state. Right now, this is just a static content handler, and it's going to serve up a file. But we could have another kind of content handler that might be like a WebMachine integration point or something like that. So once that happens, then we know that this request has been processed, or this particular frame has been processed, and the handler is off handling its business. So we just transition basically back into this. We're ready to receive more frames on the connection level. So that's cool. That's multiplexing like in a nutshell. There's plenty more to it. But I want to introduce this idea of flow control. It's another thing that's really cool. We can actually tell a client or to stop sending us data. We literally cannot handle it right now. So this only applies to data frames. And what's cool about this is like we can send control frames over the connection and not have to worry about these limits. So if you need to reset a stream to basically kill the stream and not keep going with it, then you can get around the data frame limits to do that. You can do connection level stuff. You can send go-aways. You don't want to be blocked with any of this. So that's why that's available. But each receiver advertises how many bytes it can actually receive. and maybe that's a memory constraint. Maybe that's just how you want to handle your business. That's fine. And a sender honors that. It won't send more than the receiver advertises. So we've introduced this concept, and there's a new frame type for that. It's called window update, and it just sends a positive integer over the wire, and that integer is saying, increase the credit that we have. I said I can receive 2 kilobytes, but I can receive 1 more kilobyte than that. So here's 1 kilobyte, the integer I'm sending to you. And now between the two of us, we both know I can accept 3 kilobytes. This works on the connection and stream level. So you can have these limits for both the entire connection and just the one stream. So how do we implement it? Well, we only have to worry about data frames, but at both the connection and stream level. So we're going to have to add some state to the stream state to actually keep track of these limits. So look at this static type handler, and I just hard-coded response types in to make sure this presentation worked. And what are you doing here? We're reading the file, we're serving it up, and then we're converting the data 2 frames. Yeah, and that's it. Why is there not more code here? Can I scroll? No, I moved it on another slide. After we have a set of data frames that we're going to serve up, pieces of this file and some headers, we're going to fold over the whole thing. And that's what's so cool about this finite state machine thing, right? Is that we know the state of it is going to be a tuple of both the stream state and the overall connection state. So if we have a set of 100 data frames, we can just fold over that and just send each one through this structure, and it's going to return as the accumulator my state for the connection and my state my state for the stream, and then my state for the connection. So that's pretty cool. And then the send frame function, since these are all data frames, it's going to go through this clause, which evaluates both the stream state's send window size and the connection state send window size, and it's going to just use this guard to say, if they are both greater than or equal to L, the length that's coming in over the frame header for the data frame, then send them. Otherwise, we're going to otherwise nothing. And we also have to decrement each of the 2 send window sizes, right? The client said you can send me 2 kilobytes. We're going to send a kilobyte now, so now we know we can only send 1 more kilobyte. So we do a decrement there to make sure we keep track of that. So what happens when that guard is false? It falls down to this clause, which says we can't send anymore. So queue it up. And I haven't queued it up yet. I've concatenated a terrible list here. But this works, and I'm going to fix it later. I left it in the slide because there's a GitHub tag to all the source that's at this version. So let's see, yeah. So queued frames, that really only applies to the connection level, but we have these queued frames, and they're sitting here in this state now. They're in the state of the stream. What do we do with them? They're just sitting there in this state. We're just holding on to them, and we don't know what to do. Well, the window update frame comes over the wire, and it says, hey, I'm ready for 2 more kilobytes now. And we go, great. So we wake up, the window update frame has a stream identifier, so we know which stream to go wake up. And then we start sending, we do the same fold again. We fold over this thing until it is no longer true, and the send window sizes have gotten too small again, so we stop. But that only works for the stream level. To do the connection level, what we have to do here is we get a connection level window update, and it's the same general idea. We maintain a send window size in the connection state, and we increment it here when we get the increment, when we get the window update frame. But there's still a to-do in this implementation. I don't know if you spotted it, I sure did. There's nothing in here that's waking up old streams. If we stop sending frames because the send window size in the connection state has gotten too small that we don't have a buffer to send, now that we have that buffer because we've increased the send window size, there's nothing in this code that wakes up the stream. So I'll do that tomorrow. So also here's prioritization, and prioritization is another feature that we've added that actually lets you prioritize streams. And it's cool because you can request priority on the client side and say, this JavaScript file is more important, or this HTML file is so important that without it, we have no DOM, so my JavaScript file is worthless. So give me the HTML first. It's a tree structure, so you can actually just have multiple dependencies on a single stream. But the most important thing is that a server doesn't have to honor any of it, so I punted. And I'll get to it. But the one thing I didn't punt on was knowing that I have to do this in the future is why I can't spawn a gen FSM for every stream. Because I have to be able to enforce some kind of priority on these streams and when they're serving responses. And if I spawn off new processes and say, just go nuts, well, I can't really tell them what to do anymore. But we do this with a priority frame. It's a new kind of frame, and it just it says, hey, here's the stream ID that I want you to change the priority on, and here it's new priority. And then there's some cool algorithm inside the spec that actually says, okay, well, if this happens, then you shuffle this up the tree this way, and you shuffle this up the tree, and then you reassign the children, and it's cool. There's lots of little ASCII art, so I like it. So let's talk about server push, because this is actually really cool in like the new technology part of HTTP2, right? The idea is that you can have multiple responses per request. You'll send one request for like index HTML. And your server, so you know what's in index HTML, and maybe it's got all these links to CSS sheets and JavaScript and stuff like that. You can start opening up new streams and sending those files, anticipating that the client will eventually need them. So each response is on a new stream, and that's what these server push streams are. Server-initiated streams have even identifiers. We talked about client streams having odd. That's how we sort of keep track of the difference. And what even does that mean? I don't know, but with static content, yeah, this is what I was talking about before. You know what's going out, so you can just start initiating all these outbound connections. Now, is this exciting for APIs? Because that's where the action is, in my opinion. Yes, anything that sends links in its response body can start queuing up things to be sending out over server push. And a disclaimer, I have not done server push yet. It is the exciting thing I'm looking forward to, but I have to lay the groundwork first. So push promise is a new frame type for this. And it is essentially, if you remember how the headers frame works, it's just the first part that says a message is coming, and then it's followed by a bunch of continuation frames, probably. Push promise is the headers frame for server push. It says the thing is going to start. It has a header block fragment that is, can fit in a single frame, and it is also followed by continuations. So continuations are useful in both those scenarios. Yes, like that. And then I'm disappointed now because this looked a lot like that other slide I had about a connection message, and I must have just destroyed it this morning, even though I said I was done with my slides. I was not. But it's the same idea. There's a push promise frame, then a continuation with an end headers, data, end stream. So without a connection, what can we even do? We can't do anything. So I started making a connection. Here's some RFC about how a connection starts. Here's some RFC about what settings frames need to go in. Here's some more RFC about what can happen if we don't get a settings frame in time. I'm not going to make you read that. I'm just going to tell you what they do. You send this string to start a connection. Then you must send a settings frame. And then you must have that settings frame responded to with an ACK, which is just another flag on a settings frame. We must get one from the client, too, because we need to know what they think about the world. And then we need to send an ACK back saying, yeah, we heard you. So there are only 6 settings. Most of them you can probably figure out from what we talked about: frame size, receiver window size, whether or not you can do server push. So we're just going to get through that quick because I'm running out of time. And then this part of section 4, which just says once that's all happened, you can actually send frames. So the first part's easy, right? We just do a handle info on the socket. And we say, oh, did we get that string? Cool. Then we go into the settings handshake state. Of course there's a settings handshake state. What does it do? Well, what it does is it sends our server settings frame. And it waits for a client frame, and it sends an ACK. And if any other type of frames come in while this is all happening, we just backlog them so we can process them after we're connected. And that looks like this, right? So we enter the settings handshake, and we're going to trivialize this code by removing the case where we got more than the preamble on this initial connection packet, because that gets a little bit more annoying, and I have code for it, but it doesn't really go up on the slide. And what we do is we set up a queue for the backlog, and then we enter this loop with this 2-tuple in as the accumulator here. And this thing is basically saying, we're waiting for 2 target conditions before the state is over: that we've received an ACK and that we've received a client's setting frame. So we just start processing packets we start processing frames and frame by frame. And what's cool with this is that you can actually read 9 bytes off the socket and go, okay, there's a frame header, and it says that its body is going to be X bytes. So read another X bytes off, and now you have this packet or this frame, and you've built it, and you know what to do with it. And if it's a settings frame, then we enter this loop where we do one thing. And if it's a different kind of frame, then we essentially add it to the backlog to process after the connection's been established. And so here's the bit where we flip the first bit over. We just check the guard. We say, when is flag ACK? We've got our ACK. So flip the first flag to true. And then this is the other one. When it's a client setting frame, that means it's a settings frame, but it did not have an ACK bit set. Then it must have settings for the client. So we're going to put those in our connection state, and now we've agreed on what's going to happen. So in developing this, I started off with this minimum viable response, right? I had this ng-http2 client for command line. It served a response, and that was great, but now what? Well, I started serving this deck over Firefox before it was even done, and I saw all sorts of things break, and my JavaScript didn't compile because my frame size was too small, and it wasn't sending all the JavaScript files, so I found a lot of bugs that way. But at the end of the day, Firefox did an HTTP2 implementation right, so I couldn't test all these error conditions in the RFC. So I made my own client, and my client can break things. I can send arbitrary frames over whenever I want and see how they break. So that's the high-level API is this, this HTTP semantic API that we all know and love. And then this mid-level API is this just sending whatever frames over I want. So I have this other case we can talk about really quick and blah, 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 blah. The tilde is, once a header frame is received on StreamX, we can only accept continuation frames from StreamX, and anything else that happens, we close the connection in a huff. Why? Because everything needs to come over in order. These are headers we're talking about, people, and headers have indexes, and these indexes all increment, and they all have to stay in sync on both sides of the connection. If we get anything out of order, then everything we know is meaningless, so we have to stop. This bit of RFC knowledge is brought to you by me, Joe DeVivo, who's been reading RFC, so you don't have to, since 2015. So here's the bad frames I'm sending off. I got 4 frames here. I got a headers frame, I got a continuation frame, all on stream 3. Then I have another headers frame. That's a big no-no. And then a continuation frame with an end headers flag set. And then I'm going to send them all over my client. And then I'm going to serve all these things like, did 0 frames come back over stream 3? I hope so. Did 1 frame come back over stream 0? Was it a go-away frame? And did that go-away frame have a protocol error inside? Well, to actually implement this, I need to create a continuation state, right? The whole connection transitions into this thing where once we get a headers frame, we go into this place where we only take connection frames. What's that look like? It looks like this. This is the continuation state from HTTP2 connection. And all it does is say, did the frame coming in, we read in the frame, is it a continuation frame? Yes. Is the stream ID in that frame match the stream ID that's in our connection state? Yes. Then route the frame. If it's not, go away, protocol error, we don't serve you. If we take out that bad frame, then we can change the test. I have both tests in the code, and you can click here. I think on this is a link. I think you can go see the source of it. Yeah, and I check stream 3 now, and I make sure it did actually respond. And I check stream 0 and make sure I didn't get any bad frames over. It didn't tell me to go away because everything's great. So we wait like 5 minutes and everything times out. But that's fine. That's okay. It's a connection. It's what it's supposed to do. So I don't know. I hope you're getting into HTTP2 like I am because it's coming. It's coming. HTTP1 isn't going anywhere, but it's coming. So thanks a lot. There's a lot more references in this deck, and you can check them out later.